All right, good morning, everybody, and welcome back. Today, we're going to take a look at classifying real numbers in our lesson, and there is an assignment posted in Schoology under the title Unit 0, Day 1 Assignment. I think it's just 4 questions, and there's a couple different parts to each question, a total of 20 points. All right, so at this point, you maybe want to pause the video and jot these things down in your notebook. We're talking about different types of numbers. So we have natural numbers, whole numbers, integers, rational numbers, irrational numbers, and real numbers, and how they all kind of fit together. These number sets are not exclusive, meaning a number can belong to more than one of these groups. So as we go through, there is also a nice diagram on the next page that'll kind of help show what that looks like. So starting out with natural numbers, those are like counting numbers. Okay, so starting at 1, if you go up by 1, those are your natural numbers. So 1, 2, 3, 4, 5, 6, 7. And that list goes on forever. So the number 1,032,000 is still a natural number. Okay, it just continues as long as it's counting by ones and not including any decimals or fractions. It's a natural number. Now, whole numbers is basically all of the natural numbers, but it also includes 0. Okay, so the number 3, yes, it's a natural number. It is also a whole number. Okay, the number 0 is not a natural number, but 0 is a whole number. Think of it as the first or the smallest whole number. Integers are positive and negative whole numbers. The only exception to that, I guess, is 0, because 0 isn't positive or negative, but because 0, 1, and 2 are whole numbers, they're also integers. And then the opposites, or the negative side of that, are also integers, like -1, -2, -3, -4, and so on. You could think of those numbers as like the tick marks on a number line. -72 is an integer. Is -72 a whole number? No, it's not, because it's on the negative side. It can't be a whole number. Is -72 a natural number? No, it's not, because natural numbers are only those positive counting numbers. Next is rational numbers, any number that can be written as a fraction, like a over b, where a and b are the integers, and b cannot equal 0. It's important that b can't be 0 because you can't divide by 0, so that can't be on the bottom. But it can be any two integers written as a fraction, like 2 over 5, 2/5. That's a rational number. 4 over 1, okay, so that's the ratio of two integers, so that would work. But 4 over 1 is really just the number 4. So really, examples of rational numbers are any of the previous number sets. So integers are rational numbers. Whole numbers are rational numbers. Natural numbers are also rational numbers. Okay, so all of these above it are also rational numbers. And the other ones that we also include would be terminating decimals. So terminating means that it ends, like 0.5 is terminating. Repeating decimals, like 0.333333333 repeating, that's a repeating decimal, which represents the fraction 1/3. Since a repeating decimal will always represent a fraction, it's a rational number. Fractions themselves, by definition, is a rational number. And then mixed numbers, like 3 and 1/5. Well, we could rewrite that as a regular, I should say, improper fraction, where we have a bigger number on the top. So 3 and 1/5 would be like 16/5. And that's then written as a fraction of two integers, 16 over 5. So yeah, that's rational also. So if it's not rational, it's what we call irrational. So any number that's not a rational number is our definition there. So what are irrational numbers then? Well, most square roots are irrational. We have to be careful. I didn't say all square roots, but most of them. For example, the square root of 2, if you were to check on the calculator, it would give you a number and show you as many digits as it can on the calculator. But technically, those digits will never end and they will never repeat ever. Okay, so the square root of 2 is actually irrational because it's not one of these rational numbers. However, the square root of 4, what's the square root of 4? Hopefully you said 2, and if you did, you're right. But the square root of 4 would actually be rational because it ends up simplifying to being just a regular number, okay? Special numbers can be irrational, or usually are irrational, like the number pi, that famously magic number that goes on forever and never repeats, 3.1415925. I think I said those digits right, but that's an irrational number because it is not rational. And then finally, real numbers are really all of the above. These are all the different types of real numbers. So any number that can be placed on a number line is a real number. If you're wondering, well, then what's not a real number? We'll get to that later this year. So here's a graphic organizer to help kind of show how that works. And you'll notice some of these circles are embedded inside the other circles. And that's because those numbers in one circle belong to both circles or all three circles, or even all three circles and a box, or even all three circles and one box here, which is part of the bigger family of real numbers. So the number like a 2, yes, it's a natural counting number, but because it's a natural number, it's also whole and an integer and rational and real. The number 2 belongs in all of these categories. And any other natural numbers would as well, like the number 7 or the number 28 or the number, my favorite number, 137. That's not really my favorite number, but it would belong to all of these. The number 0, now that's not the only whole number, but it's the only whole number that's not natural. So 0 is a whole number, an integer, a rational number, and a real number. Integers, all of these numbers in here are integers. So natural numbers, whole numbers, those are all also integers. But then there's even more like -2, -5, -7, -32, -78, -642. Those are also integers, but the negative integers are not whole numbers or natural numbers. Okay, so it's kind of a layered approach. Rational numbers, so all the circles are rational numbers, and anything inside here, but there's more than that. There's those terminating decimals like 0.5. There's the mixed numbers like 2 and 7/9. There's repeating decimals like 5.3, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. And then those irrational numbers that include square roots that don't simplify, magic numbers like pi and e. All right, so hopefully that helps a little bit with those different number classifications. I want to go through a couple of examples that might help as well. So the number -5/2, and we're going to try to classify this number into these categories. Remember, it's not just it belongs in one, it can belong in more than one. So is it actually I want to start with, is it a real number? Yes, obviously it's a real number. It can be placed on the number line. It's like -2.5 if you were to divide it out. Is it a rational number? Let's see, rational number can be decimal, terminating decimals, repeating decimals, mixed numbers, fractions. Well, yeah, it's a fraction. So it is definitely rational as well. Is it an integer, like these numbers inside here? Can a fraction of -5/2 be an integer? No. So that's kind of where it stops. It's a real number and it's rational, but it's not an integer, it's not a whole number, and it's not a natural number. And then since it's rational, it's not irrational, right? You'll notice those two boxes don't overlap. Numbers are either rational or irrational, but not both. The number 0, um, certainly it belongs over here. It's on the rational side, so it's a real number. It's rational. Is 0 inside the integer circle? Yes. Okay, because whole numbers are inside the integer circle, and 0 is a whole number. So it ends up being real, rational, an integer, and a whole number. The next one, 0.5129. Well, the minute we start as a decimal, we can eliminate it's not natural, it's not whole, it's not an integer. So it's not one of the circles. Okay, if it's a decimal, the first category it can belong to is rational. And in this case, it is a terminating decimal because it ends. So yeah, that's fine. It is rational, which makes it real also, because rational numbers are part of the real number family. Next, we have a repeating decimal, 0.6, like 0.6666666, repeating. So that, again, is a type of decimal. Repeating decimals are rational, and rational numbers are real numbers. So same two categories. We have the square root of 2. I kind of gave that away earlier, but the square root of 2 is irrational because it's a square root that kind of, as a decimal, goes on forever and never repeats, which also is still a real number. Okay, so irrational numbers are still real numbers. So pretty much everything's a real number. And then you have to decide, is it rational or irrational? And if it's rational, we have to decide, is it an integer? If it's an integer, is it also a whole number? And if it's a whole number, is it also a natural number? Next, we want to take a look at the three statements below and decide, is it always true, sometimes true, or never true? This is similar to what you'll do in your homework today. An integer is a whole number. So let's see, integers are the big circle. Whole numbers are inside of that circle. So the statement, an integer is a whole number, well, it is at least sometimes true, but is it always true? Are all integers whole numbers? And the answer there would be no. It's only sometimes true that yes, an integer can be a whole number, like the integer 3. 3 is an integer, 3 is a whole number. Okay, but what about the integer -2? Is -2 a whole number? No, because it's outside of the circle. So that statement's only sometimes true. Next, a natural number is an irrational number. Let's see, natural numbers are those counting numbers. Are those numbers irrational numbers over here? No, those do not overlap. There's definitely a dividing line between those. So we would say never true for that one. Last statement, a rational number is a real number. Let's see, rational numbers are all the types of numbers inside this box, all the numbers inside the ovals, all those decimals and fractions. And are those numbers real numbers? Yes, absolutely. A rational number is always a real number. All right, we'll do just a few of these and I think we're done. So we'll look at, this time we're given the number and we're going to check the box. Let's see, the square root of 2. Things are organized a little differently on our table. Is the square root of 2 a counting number? No, we don't count by square root of 2. So is it a whole number? No. Is it an integer? No. Is it rational? No. Is it irrational? Yes. All right, 7.444 repeating. So the 4 repeats. And we know that repeating decimals are not natural, whole, or integers because those can't contain decimals. Rational numbers is the first time we get into those decimals, whether they're terminating or repeating. The fraction, negative 51 seventeenths. At first glance, well, we see it's a fraction, so we know it's rational, not irrational. We have to check, is it also an integer or a whole number or a natural number? Well, let's see. It looks like it's just a fraction, but 51 can actually be divided by 17 evenly. This actually ends up equaling -3 when you simplify it, okay? -3. -3 is an integer. Integers are like our number line numbers when you count by ones, so positives and negatives, or positive and negative whole numbers. So yeah, it's an integer, but it's not a whole number. Whole numbers by definition are 0 and the natural numbers, the counting numbers. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but not the negative side of things. So it's a rational number, it's an integer. All right, one more. 3.95, that's a decimal. So we know it's not any of these first three. It's not natural, it's not whole, it's not an integer. But 3.95 is a rational number because it is a terminating decimal that ends, right? It's just 3.9500000000. Okay, so the digit ends at 5. So it's just rational. And of course, all of these are real numbers as well. All right, so that's classifying numbers. Your assignment's posted in Schoology, Unit 0, Day 1. I would encourage you to go ahead and try that right away. You could go back to this video at any point if you need to see examples similar to ones in the video.